for equilibrium. And we're going to talk about our constant Kw in this case. Last week we talked about Kc, equilibrium law constant for reactants and products. We're going to specifically focus on water today and talk a little bit about that. So pure water has very slight electrical conductivity. Therefore, some of the dissolved ions must be present, or some dissolved ions must be present. We know in order for a solution to conduct electrical conductivity or have electrical or conductivity, we have to have a little bit of ions there, pluses and minuses, right? A small amount of H3O plus, which is known as, of course, the hydronium ion, yes, and hydroxide ions are present because of the autoionization of water. When you look at water, I'll give you two different looks at this here. When we think about water, water is, once again, liquid here. When we think about water, we think about H2O, molecular compounds, sharing electrons, etc., etc. Some of those water molecules are able to what we call autoionize, or basically ionize, all right? Which means basically you're going to get some H plus ions and hydroxide ions at times, okay? So they're not all stuck together as H2O, right? H2O, by the way, they're not all stuck together kind of looking like this, right? So they're not all stuck together like that, sharing electrons, etc., etc. Don't forget, though, water is polar. Some of these, before we get to that, I guess, H plus, this can break up into H plus and OH minus, of course. Water is polar as well, don't forget, right? In fact, it's got hydrogen bonding, yes. It is a polar molecule, though. So all these things take place here. All these things are happening. Now, don't forget, with acids, all right, we talk about hydronium ions and things like that, but that's basically what's happening with this water. It breaks up into H plus and OH minus. However, if we were going to talk about this, we would call this Arrhenius' definition from Chem 20. Arrhenius' definition of an acid and a base. In this case, remember, for every water, you get an equal amount of H plus and OH minus, which is an acid and a base. Therefore, it's still neutral. That's why when you drink water, if you did actually ionize some H plus and OH minus, it wouldn't harm you because we have equal concentrations of H plus and equal concentrations of hydroxide, and they basically neutralize each other out, okay? And we're going to talk a little bit about that coming up here. Another definition we could use, let's use this one here, is the one where it reacts with water. So if we said this plus water would also give me H3O plus and hydroxide, and this, of course, would be Arrhenius' modified definition, modified Arrhenius theory definition from Chem 20, produces hydronium ions. How do you get a hydronium ion from Chem 20? You get an H plus that's attracted to this water polar molecule, right? So H plus attaches itself to a water molecule, and we get H plus water, H3O plus, hydronium ions. Why do we need to know that, or why do we talk about hydronium ions? Remember, after much research, they said, hey, let's look at some water. So they looked at water and they couldn't find, or let's look at some acids, and they couldn't find anything such as H plus ions by themselves. There was no such thing. So Arrhenius said, I'm going to modify my definition. I'm going to react it with water. And what they did find was that any H plus ions actually attach themselves to water, H2O, to get H3O plus. Okay, do you guys remember that from Chem 20? If not, well, I'm telling you now. So H2O with an H plus gives you what we call the hydronium ion, H3O plus. If you're going to write this one out here, it is not balanced. So that's why you're going to see a 2 in front of here, basically. H2O would react with an H2O to give you H3O plus and hydroxide. Remember that H3O plus is responsible for all acidic-like properties, and hydroxide is responsible for all basic properties. All right? All acids need to produce H3O plus. All bases have to have OH minus. Yes? In water, you have acids and bases. You have a combination of them. Okay? And once again, not very many of these will happen. Okay? But some will ionize into these two ions. the next part here tells you basically how many will that happen. How many will ionize. At 25 degrees Celsius right here, guys. Don't forget that's what Kelvin is. 298.15 is about 25 degrees Celsius. At 25 degrees Celsius, if you had water, you would have these following concentrations for these two ions here. 1 times 10 to the negative 7 and 1 times 10 to the negative 7. Remember, those two concentrations would be equal, of course, because they react in a 1, or they're basically breaking up into a 1-to-1 ratio. Okay? So for every H3O plus ion you get an equal number of hydroxide ions, and therefore the concentrations would be equivalent to each other. Okay? Now, what they did here was they said there's a special relationship that happens for water. Okay, not same as the other day. The last day we said if we wanted to find Kc values, for example, we would take the products, right? The concentration of the products over the concentration of the reactants, right? And we raise them to certain powers if it was part of the coefficient and things like that, right? Yes? Okay. We calculated Kc, I gave you Kc, you calculated concentrations, etc., etc. The exact same thing is happening today, but we're not going to call it Kc because it's specific for water. So we have what we call the equilibrium constant for water. Now, if we do the same thing with this one, look. If I look at this equation here, right here, okay, what are we doing? We're taking H3O plus, concentration of H3O plus and hydroxide. Okay, there's your products, yes? So the products raised to the 1 power, of course, over the reactants. But I don't write down this one. Why not? Why don't I write down this? What? It's a liquid. What's the other one we don't write down? Solids. So we don't write down liquids or solids. So when I go back to my Kw here, I'm done. Okay, I don't have to, I could put this over, I guess, you know, if you want, you can put this over 1, but you don't have to. So Kw is equal to those two multiplied together, the hydronium ion concentration and the hydroxide ion concentration. And at 25 degrees Celsius, the Kw, of course, is going to be 1 times 10 to the negative 7 times 1 times 10 to the negative 7. And Kw works out to be 1 times 10 to the negative 14. Always at 25 degrees Celsius. Okay? So I know that my equilibrium constant for water in this case at 25 degrees Celsius always has those two concentrations there for the hydronium and the hydroxide. So I know that it's always going to be 1 times 10 to the negative 14. We're going to use that basically. And now that you guys this year maybe have taken some math, you guys will know that if you take logarithms or things like that, it's on base 10, right? So look, here's 10 to the negative 14. Logarithms, if we take negative log of 10 to the 14, negative 14, we get 14, and that's your pH scale. That's where that comes from, based on pure water at 25 degrees Celsius. 1 times 10 to the negative 7, 1 times 10 to the negative 7. That's why the pH of neutral water is 7, okay, based on that logarithmic scale. And that's because the pH is 7, the pOH is 7 as well, if you remember from Chem 20. Those are both 7s, right? If you put this in your calculator, negative log of that, you'll get 7. And if you do this for the pOH, you'll get 7, okay? And that's why the whole scale is built on a 14 scale, 0 to 14, because those are the concentrations at 25 degrees Celsius for each one of those ions, okay? So that's what it basically tells you here as well. So Kw is 1 times 10 to the negative 14. We're going to use that to help us today to figure out other concentrations. Acids are substances that ionize in water to produce H3O+. You will still have some hydroxide in that because, of course, H3O or H2O will break up into H3O+ and hydroxide. But with acids, this concentration is going to be higher than 1 times 10 to the negative 7, the hydronium ion. And the hydroxide concentration is going to be less than that, okay? 1 times 10 to the negative 7. Basically, they're telling you that those are the pHs basically that are going to be involved. In bases, substances that ionize to produce hydroxide. In this case, the hydroxide ion concentration is higher, 1 times 10 to the negative 7. You still have hydronium ions, some hydronium ions in there, but it's not going to be the same as the hydroxide ion concentration, which is much, much higher. So you're still going to get some hydronium ions. There's still a little bit of acid in there somewhere, but the hydroxide ion is going to be much, much more favored, of course, or much higher. So that's still going to be the case. The hydronium ion concentration will be less than 1 times 10 to the negative 7, basically. All right. Two formulas, of course, that you could use. If I know that Kw from the other page here, guys, if Kw is this formula here, right? Products over the reactants. I just told you that, basically, on that little example I did. If I know that that's the formula, I can use that to figure out the other concentrations, Kw, right? So if I want to solve for this, I'm going to divide both sides by OH, and I'm going to get this formula here. And if I want to find OH, I divide both sides by H3O+, and I get that formula there. All right? So we're going to use that now to calculate some concentrations on the next page here. Okay? As a strong acid, HNO3 completely ionizes in water. Calculate the H3O+ and the hydroxide ion concentration of 2.5 times 10 to the negative 3 moles per liter HNO3. Okay, so you need to find both the H3O+ concentration, probably fairly high in this case because we're talking about an acid, and also the hydroxide ion concentration, which is probably going to be fairly low, because if the H3O+ concentration goes up, the hydroxide ion concentration is going to go down. Okay, because remember, multiplying those two together, they still have to work out to be 1 times 10 to the negative 14. This is review from last year. That's what we're doing, except for the only difference between last year and today is you're going to use Kw values as well to help you solve. Other than that, the formulas are all the same that you did before, so this should be review for you mostly. What do you know about strong acids? I mean, it tells you right there, but I want somebody else to say it other than me. What do you know about strong acids? What happens when you put a strong acid into water? Yeah. They do. How much do they fall apart or break apart? What? Very easily, yes? You would say 100%. Strong acids completely ionized, yes? That's what it says right there in the notes for you. Strong acids completely ionized. That's important, okay, for today. And it's also going to be important for tomorrow. Tomorrow's my favorite lesson. Love tomorrow. Weak acids and weak bases. Fun equals data booklet. That's how we spell fun. Yeah. So, with this one here, though, this completely ionizes. So what does that mean? It means the following. It means if you take some HNO3, okay, and you're going to, now I'm going to write out the entire thing here, but HNO3, and we did this in Chem 20 if you remember, and this is kind of what you need to do, you know, this is so you kind of understand what's going on here. If we're going to do modified Arrhenius theory, so the whole kit and caboodle here, HNO3 with water reacts with water to give me single arrow, because it completely breaks up, right, completely ionizes, into H3O+ and nitrate is what you get when you put HNO3 into water. Okay? Remember, for modified Arrhenius theory, we react it with water to produce hydronium ions, H+ ions added onto water, and of course, nitrate. It tells me that my concentration here for this one was what? 2.5 times 10 to the negative 3 moles per liter. So this is something we would have done in Chem 20. Write down that. Okay? That's pretty much all I'm told in this case, I think. Yes? And I need to calculate the concentration of this. Basically, they say, what is the square brackets H3O+? What is the concentration of the hydronium ion? And this is not a trick question, right? But when you write it out like this, you know that for every one of these, reacts with one of these to produce one of these and one of those, yes? So, because it's a strong acid, and this leads into tomorrow, because this one is a strong acid, it completely ionizes. AKA, for every one of these that I use, I get one of these, yes? Right? So if the concentration is H of HNO3 is 2.5 times 10 to the negative 3, then the concentration here is 2.5 times 10 to the negative 3. And I wanted to write that out for you guys so that you please understand that. For strong acids, that's the case. We're going to be writing out lots of these equations. Okay, you might as well get used to them. So, that's the concept. I mean, I'll just do it here, but same thing, right? Obviously. The concentration of the hydronium ion is 2.5 times 10 to the negative 3. That's what happens for a strong acid. It's a one-to-one relationship. Breaks up, ionizes completely, 100%. Okay? Or approximately 100%. We say it's 100%. Basically, everything ionizes. Everything turns into ions. Yep. No, but this is the concentration of the acid that I'm using. Okay? So we're not going to, this is not pure water anymore. Okay? This is a concentration of acid. Now, how am I going to find out the hydroxide ion concentration? Because they also want to know what's the hydroxide. And this is obviously an acid, so why are we talking about hydroxide? Once again, there's going to be a little bit of hydroxide in here because we do have some water that, once again, automatically ionizes. So what is the hydroxide ion concentration going to be? Well, it's probably going to be way less than that because it is a strong acid. So I'd expect the concentration of this strong acid, that's quite strong. That's going to override the hydroxide, of course, but there is going to be some hydroxide concentration in here. Okay, what is that going to be equivalent to? Well, let's take Kw and divide it by, of course, the hydronium ion concentration, or 1 times 10 to the negative 14 over 2.5 times 10 to the negative 3. Don't forget brackets there for that, because otherwise you're going to be doing the wrong order of operation. So let's see, that should work out to be, where is it here? 4 times 10 to the negative 12. Oops. Let me just fix that there. Okay. So that would be your hydroxide ion concentration. There's your hydronium ion concentration. You can see 4 times 10 to the negative 12, quite low, obviously. Okay, but we basically spiked up the H3O plus concentration by adding acid to this solution here, to this water. Okay, so we're going to get used to writing some of these equations because that's what we're going to be doing in this unit. We're going to be talking a lot about acids and bases, and strong acids, and eventually tomorrow weak acids and bases. Okay, so tomorrow's probably a pretty important day, actually, but it's fun for me. Probably for you, too. I have to assume so. Next one. Let's take a look at a base now. Let's take a look at this base. A solution of sodium hydroxide is going to be made by dissolving 1.6 grams of sodium hydroxide into 5 liters of water. Calculate the H3O plus and hydroxide ion of this solution. Once again, we're talking about a base here, sodium hydroxide. Remember, all bases form hydroxide ions. So I'm going to assume out of these two, the hydroxide ion concentration should be quite high in this one, and the hydronium ion concentration quite low, of course. So what's the first thing you need to do? Well, probably, you might say, do I need to do this? And I would say, yeah, you probably should understand that when you put sodium hydroxide into water, you get sodium ions and hydroxide ions. And you might even say, do I really need to do that? Is that something that I need to worry about? And I would say probably is, yes. You probably do need to write that equation out. This one is a 1-to-1-to-1 ratio, but they're not always. If you talk about barium hydroxide, it's a 1-to-2 relationship. So you probably should start with equations for both acids and bases, and we're going to do that for the rest of this unit. So it's kind of important. It says you're going to use 1.6 grams of this, and we're going to put it into, what was it, 5 liters, I think? Is that right? Somebody? 5 liters of water. Okay? And once again, I want to know, it says find the hydronium ion concentration and the hydroxide ion concentration. So I want to find that. If I want to find that, this is Chem 20 all over again, guys. In fact, this isn't even Unit 4 of Chem 20. This is Unit 3. Okay? This is finding concentration of individual ions, yes? That's what this is called. We do this in Unit 3. How do I find C there? What do I need? N. How am I going to find N over here? How do I find N? Yep, but I don't know C. Use the molar mass here, yes? So I'm going to use the molar mass here, 40 grams per mole. And I'm going to find N. Okay? And I believe that worked out to be 0.04 moles. Yes? So, using those two there, it's going to work out to be 0.04 moles. If I know that, for example, 1 mole of this makes 1 mole and 1 mole, for every 1 sodium hydroxide, I get an equal amount of hydroxide. If I get 0.04 moles here, then it's going to be 0.04 moles there. Okay? Concentration of individual ions, basically. Now I have N and V, and I can find C by dividing those two. When I divide those two, I will get 0.008 moles per liter as a concentration. Okay? Actually, I guess I should technically have 0.0080 probably for significant digits, I guess. Maybe I better do that, since we're going to talk a little bit about significant digits here today. I guess that would probably be the best answer, because remember, the zeros in the front don't count, right? So zeros at the end do. So we probably should have 2 there based on this. Okay? So that's my hydroxide ion concentration. Yes, that's just review. That's Chem 20. That's nothing special. Then, so I know this is, like I said, moles per liter. And now this year we're just going to say, okay, what would the hydronium ion concentration be? Because there is going to be a little bit of acid in here, of course, with the auto-ionization of water. What's that going to equal? Well, I'm going to take, once again, my Kw expression. So Kw over the hydroxide ion concentration should do that for me. 1 times 10 to the negative 14 over 0.0080. And doing that, I should be getting, let's see, all said and done here, well, it's 1.25, but significant digit-wise, we're going to go with 1.3 times 10 to the negative 12. I'll just double-check that, moles per liter there. That would be your hydroxide, or sorry, your hydronium ion concentration. Times 10 to the negative 12, yeah, okay, is what you would do for that. So really the only thing different from last year was we introduced this Kw as far as that goes. Okay? So, like I said, all right, moving on here now. We're going to talk a little bit about a little bit more review from Chem 20, pH and pOH, of course, and there's formulas that calculate those for you. But a pH scale typically runs from 0 to 14, of course. Once again, as always, pHs of less than 0 are possible, and pHs higher than 14 are possible. Okay, and I've told you this, I say this all the time in Chem 20, we have acid that's in the room. It's not like special condition. We have acid that has a pH of like -1 something. Okay, so it's not like it's such an anomaly. It happens. Okay, this is just a basic scale, 0 to 14. 0 to 14, why? Because water, okay, think about this. Water has 1 times 10 to the negative 7 hydronium, 1 times 10 to the negative 7 hydroxide. Those two multiplied together gives you a Kw value of 1 times 10 to the negative 14. pH is a scale from 0 to 14. Because pH, you use the negative logarithm. Logarithms are a base of 10. So when you have, for example, 1 times 10 to the negative 14, isn't that really just 10 to the negative 14? Right? Yes? And since logarithms are a base of 10, if you take the logarithm of 10 to the negative 14, well, if you take you know, we put the negative in there to switch it from 10 to the negative 14 to 14, yes? That's why the negative's out in front of the logarithm. If you didn't have the negative, you'd have negative 14, yes? We changed it to a positive scale, that's all. So the negative is there to change the negative 14 into positive 14. The logarithm, it changes it from a base of 10 to the actual number. That's where that comes from, okay? You guys are doing logarithms like Math 30, or if you haven't, you will be soon, should be, okay? So that's where that comes from. And that comes from based on the fact that at 25 degrees Celsius, 1 times 10 to the negative 7, 1 times 10 to the negative 7, you multiply those two together, 1 times 10 to the negative 14. So that's the scale we're working with, 0 to 14. Okay? So once again, is that always the case? No. Could be lower, could be higher than 0 to 14. Here's two formulas that, of course, you guys know from Chem 20. If I want to find the pH, I take the negative log of the hydronium ion concentration. And if I have the pH, and I want to figure out the concentration, I go 10 to the negative pH. These formulas we gave you on the back of the periodic table, you know, the old ones there with the big sheet, the 11 by 17, we give you those. You don't have those anymore, so you need to make sure you memorize those. Yes, you need to know those. They're not in your data booklet, and that's all you get. So make sure you know these, right? The number of decimal places in pH values is determined by the number of significant digit figures in the H3O plus concentration. I don't remember if you, or I don't know if you remember this part, but when we talk about concentration, if the concentration, let's say, has 2 significant digits, what is the pH correlation with that? You guys remember? The concentration had 2. What does the pH have? You remember? I'll give you a hint. Still 2, but there's a little amendment to it. 2 after the decimal, right? We're going to do some examples. I'll show you. Here we go. Calculate the pH for the solution in which H3O plus is 2.7 times 10 to the negative 5. So we're calculating the pH of this, 2.7 times 10 to the negative 5. So your options are, or I guess if you're looking for, you know, which formula do you want to use for this question here? Those are your 2 options, of course. Which one? Left one or right one? Read the question. Somebody pick left. Okay, you're looking for the pH. So you're going to put pH is the negative log of 2.7 times 10 to the negative 5. Yeah. And you will get for, let me just double check here, 4.5686, I think, right? 4.5686. Now, good so far, I think. Is that right? Unless I picked it around. No, that's the right one. Okay. Then you have to do significant digits. So remember, how many significant digits are in my concentration here? 2, right? 2 in my concentration. So that means you, for pH, have to have 2 after the decimal. Remember that 4 is not significant. So 2 after the decimal, 5/7. Those 2 are the ones that are significant. Okay? Those 2 match up with those 2, if you want to say it like that kind of thing. 2 in the concentration, 2 after the decimal. And if the pH is 10.46, well then only the 4/6 is significant. Only, I don't care what number's in front. It could be 0, -1, 10, 12, 14, 15 in front. I don't care. It's only after the decimal that's significant for pH. Okay? So that's how you would do that one there. What is the H3O plus concentration with a pH of 10.33? So I guess we'd have to probably use the other formula in this case, right? We're looking for the H3O plus concentration, and we know we're going to take 10 to the negative pH, right? So 10 to the negative 10.33, and you will get, let's see here, I don't think I actually have that one there. Let's see. 10 to the negative 10.33. 4.667, oh no, 4.677 times 10 to the negative 11. That will be in moles per liter, of course, because you are finding the concentration. Significant digit-wise, what do we need to have? Well, how many significant digits in 10.33? 2. Only the ones after the decimal count. So 2 there. So how many do I need here? 2. So we're going to round it up to that. Okay? 4.7 times 10 to the negative 11. All right? Now, let's look at some real questions now. POH and pH. Don't forget, POH refers to hydroxide, pH refers to hydronium, right? I make a big deal about this in Chem 20. So, for example, if I was doing this question here, and it said, calculate that with the pH of 10.33, do those two go together? No. So you got to do a little bit extra work, right? You got to convert it. Yes? And in Chem 20, you guys learned there's something to do with pH and POH have to add up to give you 14. Yes? Remember that? So we're going to talk a little bit about that, and we're going to talk about a different way to do that as well. Same formulas apply for POH, of course, negative log of the hydroxide. If you're looking for the hydroxide concentration, you take that, sorry, that should have been 10 to the negative POH. It's right on your thing there, just didn't convert over. Calculate the pH and the POH when the H2O plus concentration is 2.7 times 10 to the negative 3. So let's go ahead and do that. I want to find the pH, and I want to find the POH, the PO. PO. For both of these, if the hydronium ion concentration, it says here, is 2.7 times 10 to the negative 3. Okay. Once again, these two go together, so I can just simply stick that into my formula here. Negative log of 2.7 times 10 to the negative 3, and I will get 2.568636236, etc., etc. And I'll come back and round that later. Okay, I'm just not going to worry about that right now. If you remember back in Chem 20, what you would have done now is you would have said, okay, if that's the pH, then the POH equivalent to that is 14 minus the pH, right? And the pH plus POH is 14, right? Remember that? pH plus POH is 14. So if I want to find POH, I take 14 minus pH. So I'm just going to do that on my calculator here. 11.43136 376 something like that, okay? And significant digits now. Once again, look back at the top there. Well, actually, you don't have to. It's right here. I had 2 in this concentration. Everything's based on that. So 2 in the concentration. I should have 2 after the decimal and 2 after the decimal. So those would be your 2 answers there. Okay. If I gave you this question in Chem 20, which I would, this is Chem 20, that's what you would probably do. Okay, I hope. In Chem 30, I would do exactly the same thing. The only thing is, if you wanted to, the other way to figure this out, of course, is if you know this is the H3O plus concentration, you could have used, sorry, that's not it. If I'm looking for the hydroxide ion concentration, you'd have taken Kw over H3O plus, or 1 times 10 to the negative 14 over, what was the 2.H3O plus concentration, 2.7 times 10 to the negative 3. and you could have figured out the hydroxide ion concentration. I'll just show you here. 1 times 10 to the negative 14 divided by 2.7 times 10 to the negative 3. 3.7037 times 10 to the negative 12. And then you have the hydroxide ion concentration. I could take the negative log of that. Okay? So if I took the negative log of this question here now, POH, negative log of that, you would get 11.43. Okay? Obviously. So, exact same number, by the way. So, you could do that with Chem 30. Now, you might say, well, I'm just going to do the first one. I'm good with that. Yeah, you probably should know both because it really depends on the question that they're going to ask. You know, if they only specifically talk about hydroxide ion concentration, well, then I would just use the KW value for that. KW, like I said, KW and the hydronium and the hydroxide thing to figure that out. So I'd be, you know, don't just dismiss that KW stuff. You still need to know it, and it might save you time, especially on a test, depending on the type of question you have. Okay, and you'll see as kind of go through with questions. Sometimes it's going to be easier to calculate the pH and then get the POH, and sometimes you might want to calculate the concentration only. Okay, so it really depends on the type of question. But those are two different ways of basically getting the same thing. pH and POH in this case here. Okay, and you might be like, that's too much work. Well, maybe it is, I don't know. But it's important to know the KW relationship either way. Okay. Once again, you know the pH and the POH gives you 14. The pH starts from 0 to 4 and goes up to 14. Basically, you get increasing, increasing acidic this way, increasing basic that way. This really should have been at the top. No, that's not true. And then the POH scale is based on same thing, 0 to 14. But remember, for POHs, 0 to 7 is basic. So this part here is true for acids and bases, and this part here is true for both of these. So that diagram's actually legit there. Remember that pH 0 to 7 is acidic. POH between 0 to 7 is basic. Okay, it's the opposite. So just keep that in mind when we're talking about that stuff. Okay, I guess that's it then today. All right, so I got some questions for you to practice KW, pH, POH stuff. Tomorrow we're going to look at weak acids and bases, and that'll be fun because it's not the same.